Yeah, hi. Welcome back to Midnight Simplified. And today's video is dedicated towards teaching us how to write full smart contract for a Midnight app. So we're going to be building a Vault app using Compact. So we're going to be writing the smart contract on Midnight. And this video is dedicated towards fulfilling the request of a few developers who have actually reached out and have been following the channel and that wants to learn how to write smart contracts actively using Compact. So if you're willing to learn stuff like this, grab your learning resources and let's dive in. Yeah. So welcome back. Here are a few requirements for you to be able to follow on with this course. You actually need to have previously set up your developer environment. I do have a few videos on the channel that teaches you how to do that. And recently, because there've been a few changes, they've been upgrades actually. I'm going to be leaving links to the in the description of this video for you to learn how to install the Compact toolchain, how to set up your developer environment again. If you've not done so, you can simply just follow them and then you get your developer environment set up or upgraded to the current version we have. Um, yes, I'll be dropping these links in the description. And also, we're going to be going through um, a few useful documentations. Yeah, one of which is this compact standard library documentation. We're going to be needing it since we are dealing actually with token transfer and all of that in our Vault DApp. And that being said, you also need to know how to write basic compact code. That's a very serious requirement, else you won't be able to follow the video. And that being said, let's dive into the course properly. So to start up the project, I'm going to create a new directory. I'm going to call it Vault DApp. So I'm going to write mkdir and I'm going to call it Vault DApp and I'm going to hit enter. Now I'm going to sit into that directory. Um, this is it. And then I am going to open it in my code editor. To ensure you guys can see properly, uh, I am going to zoom in a bit. So I'm sure my screen is much more um visible right now. So you can see we are starting from a blank template, and I'll be using Born as my package manager. I would also be leaving a link to install Born in the description of this video. So since I already have Born installed, I'm just going to go ahead and run Born in it. Hit enter, and then select blank, and then it's going to install just the boilerplate with our package.json for us. Initialize our project with the package.json. Now that we have that, I'm going to close my terminal and then open my package.json. First off, before I start developing, I want to set up some do some chores around the project. So it involves certain scripts that will allow us to be able to compile our compact code without actually having to retype the command ourselves. So first of all, I'm going to initialize the script and then I'm going to call it test compile, and then this is going to be a command that actually calls our compact compiler, say compact compile, and then since this is a test script, it's going to compile our compact code without generating those zk materials. So I'm going to add this argument dash dash skip dash zk. So that's what this tells you to do. It tells it to skip generating those zk materials, and then I'm going to specify the path to our compact file. For now we don't have that, so I'm going to quickly create a source directory inside of our project. Now that we have that, I'm also going to create a new file, and then I'm going to call it vault.compacts, and then I'm going to hit enter. Now that we have our compact file, our main compact file, we can specify that path, say source /vault dot compact, and then we want to also specify a directory we want the compile artifact to be generated into. So that's I'm going to say generate it inside of my source directory, and then inside of a new folder called managed. And then if it cannot find this managed directory, it's going to create it and then generate all of those artifacts inside of it. I'm also going to add my main compile script, and then it's just going to be a duplicate of this. Is this here, and then I'm going to take out this. So this is a compile script to actually compile our smart contract. And I'm going to take out this comma. And most importantly, we're going to take out this argument here. So it just compiles it, including the zero knowledge materials. Now that we've done this, let's go into our Vault compact. Now we can start writing our smart contracts. And then let's test to see if our setup actually works. I'm going to write pragma. This is the first line you get to write when you are trying to write a smart contract. And then you want to specify the language version with it. I'm going to say pragma greater than or equal to the specific language version I want to use, 0.22.0. This is the latest compact version, and it goes hand in hand with 0.30.0 version of the compiler. So you want to install that. After this, I'm going to import the compact standard library, compact standard library. And what this allows us to do is it allows us to use a lot of inbuilt compact circuits, like the circuits we're going to be using to send token in and out of our contract, and even to receive tokens into our contract, and also a lot of ledger state declaration helpers. So we need it. It's very important. It is also complementary to this documentation. I'll be dropping a link to it in the description of this video. Now let's get started without wasting much of our time. If you're building a Vault application, what are the case scenarios you want to think of? First off, you want to allow users be able to create a Vault position, because that's the way it works in the reward, and it's only logical we have a replica of that on chain here. So we have a circuit to create Vault position. I'm going to define that by saying export, since we want user to be able to access it of call the circuit. So we're going to export it. So we're going to call it export circuit, and then we're going to say create Vault. And then this circuit returns nothing, and then this is where we write our circuit body. And sometimes you're going to hear me interchangeably call them functions. Just think of them as the same thing. So we also want to have another circuit that allows user to deposit once they've created their Vault position. And here we have the circuit. And lastly, I'm just going to copy this and delete it. We also want to have a circuit that allows users withdraw from their Vault. So these are the three circuits that are very, very important to this contract. You can expand it as you deem it necessary, but these are what we'll be going with. So just to test that our script actually works and our environment is set up properly, I'm going to try to compile this code. So I'm going to run bourne test-compile, and then I'm going to hit enter. So what this does is it has compiled our code. You can see it compiled the vault.compact contract into this our managed directory. We didn't have this here. It was generated recently. So you can see it has all of those TypeScript derivations that were made from our contract. So now that we are sure that it works fine, I want to close that side of code editor, and so we can zoom in more. So next up, what we want to do is we want to define ledger states that you can use to track Vault positions, right? You also want to declare ledger states that allows you manage tokens. Okay, so let's go on with the first part. I want to create a ledger state that allows us to track Vault positions. So export ledger state, and then I'm going to call it vaults, simply because it tracks all our vaults. And what is this state going to be? It's going to be a map. And we know what maps are in compact. They are more like hash tables, array of arrays. Allows us to store each vault in relation to the ID of the vault owner or the user's ID. You get. So we're going to say bytes 32, and we're going to have a vault structure. So we have to define this vault structure, and then we can come over here and say export struct vault as well. So this defines the nature of our vault, and then it's going to have several feeds. First off, you want to have the balance of the vault, very important. So I'm going to call it uint64, and then have a colon after that. Very important to add all of these colons. You can see I keep adding colons at the end of every line. Very important, else your compiler is going to throw an error. So we have our balance. We're keeping track of our balance. We also want to keep track of, let's say, the time this vault was created. Created at, that's just an extra, uint64. And lastly, we also want to have one extra feed. These are very minimal fields. So we want to have an extra field that keeps track of the coin color. We'll see why in a bit. Bytes 32. So for the coin color. Now we have this extra field called coin colors. This is a very minimal contract. Let's be aware of that. So why we have this coin color, it's simply because on Midnight, tokens or currencies are identified by a byte string called a color. So that's the way you can differentiate one token from the other. Say for instance, let's take for instance, we're talking about USDT Ethereum. On Midnight, each of them will have a different coin color. So that's the case here. Now that we have our what defined, we can go on to start creating our vault positions. But one thing that is also very important is when we're talking about a Vault DApp, we need users to be able to deposit tokens, actual tokens, into our smart contract. And if that is not enabled in this smart contract, then there's no point writing the contract. So we also want to be able to keep track of that. Now, usually when you're dealing with an unshielded token in a smart contract, then the contract automatically helps you manage the token and then gives you access to some utility functions that allow you manage balance. But in this case, we're trying to build a shielded vault application. So when you're dealing with shielded tokens, you have to manage the balance of all UTXOs by yourself. You get? So we have to do that. We have to declare a ledger state to keep track of that. So export ledger state, and then this is going to be called balances. I'm calling it balances because we want to go step further to allow users deposit any kind of token into the vault. Because usually you don't want a person just depositing just a single type. Then it's the contract is not usable by everybody. You have to start developing and deploying a single contract for each of them. So we're going to have a map as well that keeps track of each token type denoted by bytes 32 in relation to a qualified coin shielded coin info. A qualified shielded coin info. Now, what's a qualified shielded coin info? Now, a qualified shielded coin info, as we can see in the documentation over here, is, let me zoom in a bit. This allows us to describe a shielded coin that is already existing on the ledger and is ready to be spent. So when you see its structure it is structure in itself, and it has 4 fields. It has a nonce field. It has the color, which I just said, very important to track of. And then it also has a value, which denotes the amount of that token stored. And it has also a Merkle index. This is very important. It tells you where that shielded coin is existing at in the Merkle tree. So usually, if we were dealing with a single token, we want to have just a qualified shielded coin info. But then like I said, we want to make it more dynamic. So we're going to leave it as it, so we can keep track of different token colors. Because if you understand how to do this, then doing for just a single coin, qualified coin info is very. So that being said, let's keep going on. Also, we now we can start creating a vault position. Now, when we want to create a vault position, we want to have a way of identifying each vault. Like we said, that we are going to map each vault to the ID of the owner, right? So we want to do that. We want to find a way of generating an ID because we don't want to store their direct wallet addresses on chain. That would be the opposite of having a shielded contract. So we want to also have a circuit that allows us generate user ID. We're going to name it this way so it's practical. User ID, and then it returns to us a byte 32. That's the ID that has been generated. And then here we can declare the circuit body. Now, what we want to do is when you're generating IDs on Midnight, most of the time you want to generate an ID from a user's secret key, which is stored in their private state. That way, you don't have to uh use a static ID that is very visible to everyone. So it's only stored in the user's private state, and they get to provide it to the contract whenever it's needed in the contract context. So we want to define just one witness that allows us get secret key from a user's private state. So we want to have this like this, and sorry, and then it returns to us the secret key, which it is able to get from the user's private state. I'm going to rush it a bit so we don't waste too much time. So this allows us get the secret key. So we're going to derive our user ID from that. We're going to use a special circuit Midnight is providing to us called persistent hash. Persistent hash. And this persistent hash is a utility circuit that it's more like a generic, and it takes arguments of the type of variable that you want to hash. So we're going to pass in a vector as the type, and this vector is an array. You know, vectors are arrays on Midnight. So we're going to pass in a vector of length 2, and then we want to pass the type values we're going to be passing into it. So by 32. Yeah. So we are going to receive the secret key. Since we are going to be using the circuit over and over again, we're going to receive the secret key wherever we are in the ID from, and then we are going to pass it here into this persistent hash. So since we said the persistent hash is going to take a vector of bonded length 2, and it's going to be byte, we have to pass in that array here. And then the first value we want to pass is just a default identifier that we want to add for every user. I'm going to call this part helper circuit, part 32, and then I'm going to say vault user. So this is just to make it dynamic, so you can actually know you can actually derive the secret key from public key or user ID. Now, then we can hash it with our secret key, which we are going to be passing into the circuit whenever we want it. And then we can return the value. So this helps us generate a user ID. And then let's try to compile our contract. See, we are still doing. I'm going to run that command again. Let's compile. Okay, we don't have any errors, which means we are doing it fine and correctly. So now that we've created a helper circuit to generate user ID, it means for every new user who's trying to call the circuit to create a vault position, we can actually create a new ID for that person. So we can say new user ID is equal to generate secret key. Right? We're calling this witness that is going to get this for us. And this secret key is what we want to pass into that contract, into that helper circuit. So we're going to say generate user ID. This is our circuit, of course, the one we are going to be using to generate user ID. And then we can disclose. Remember, I said when you're dealing with witnesses or params, you want to disclose them. And we can disclose the result of this get secret key. And then here we have our new user ID. Now we can also then create a default vault position, an empty vault position for that user. So const const okay, we want to just even make it very easy. Say vaults dot insert. And then we want to insert a default vault position for this person. So just let me separate it. Empty vault. Let me just call it empty vault. Then say it's equal to, it's going to be a default. It's going to be a default vault. Now, what this default does is it generates it generates the default value for that particular structure you are passing into it, that structure type. So what this is going to return to us is going to return this vault, but with the default values of each and every of these fields. So it's going to be a vault with balance 0, rated at 0, and the coin color 0. So as opposed to that, we want to collect the coin color, the type of coin color this person wants to store inside this vault, right? So it's bytes 32, right? And then also, yes, that's all we need. We can then say, instead of doing this, what we can do is say we want to create a vault, and then this vault is we are taking balance as 0, right? And then we are setting our coin color to be equal to the disclosed value of this color the user specified that it store inside of. So this, and then created that we also might want to define time was. So for that, we can either collect the time as a parameter inside of here, or we can use a witness to get the time. Witness get current time, and this returns uint64, and then we can just call that here, disclose get current time. That's it. It should be a comma instead, and this is it. So we've created an empty vault for this user, and we can insert it inside of it. So we have a new user ID. We also have an empty vault for particular user. But first up, before inserting it, we want to make sure that this user does not exist previously. So what we want to do is say we want to assert and say we want to make sure that our vaults, we're saying this guy is not a member of these vaults before. So that's what this means. This vaults.member member is a method on vaults being a map. So as a mapping as vault being a mapping ledger type, we have access to this method on it dot members, and then we are saying it's going to return a boolean. So we want to make sure that we are checking for this guy, but then the result is not true, which is to say that this guy is not a part of the vault already. If this guy is a part of the vault already, what we want to do is say already exists. I'm just going to just have an error message here. So we're going to make sure that this user does not already exist, and then we're going to, if that is true, If this user does not exist, we're going to create an empty vault for that user, so we don't override previous user. Then we're going to say new user. That's the key we want to pass, and then the value is going to be empty vault. So at this point, we have been able to create a new user ID, create a new vault position that is empty, and also inserted it into our ledger state. So with this, we've been able to create a vault, right? So we want to go on to allow users deposit um um tokens into the contract after they've created a vault. So when the user wants to deposit, they have to pass in the coin they want to deposit. So in this case, we are going to define the coin as a shielded coin info. Now, what's a shielded coin info? Let's take a look at the documentation. So a shielded coin info, I think it's directly about this. So, a shielded coin info describes a newly created shielded coin used in outputting shielded coins or spending or receiving shielded coins that originate in the coin transaction. Which is to say, this allows us to take a specific coin from, define the structure of a specific coin that is coming from a user's wallet into our smart contract. And then, as opposed to the qualified shielded coin info, let's look at the structure. It has 3 fields instead of 4. It does not have a Mercury index, but it has every other fields. And then you can see that it's used in relation to or many circuits. We're going to be looking at these circuits in a bit. So now let's continue defining our deposit. So when the user wants to deposit, they have to pass us the coin they want to deposit, and then we want to disclose that coin since it's shielded by default. Let's call it. I'm going to add underscore before this, so we're following the same pattern. And then I'm going to call this coin. Then it's equal to disclose. Disclose. So we're going to disclose this coin the user is passing to us, right? So that's it. We've collected the token, but this is not enough because at this point we are just disclosing it. We haven't actually received this token into our contract. Now, before we receive the token, first off, we want to regenerate the user's ID. Want to regenerate the user's ID, and then that's going to be just the same way we were generating this ID previously. We're going to call our generate user ID and circuit, and then we are going to pass in the user's secret key we're able to get from their private state. Now, before we even go on, right, let's try to compile our code and see if we're having any errors. See, okay, we're having an error. We're having an error. This error is coming from line 38, simply because we didn't close this place with a semicolon, which is why I always keep emphasizing on closing your code lines with semicolon. Now you can see we've taken out the error. See, now we are sure we don't have any errors. Let's keep going. So we are going to regenerate that user's ID, and before we deposit it, we want to make sure that we are not trying to deposit tokens for a ghost user. So we have to check that this user actually exists. So assert, then it's going to be we're going to check that this user actually exists in this case now, not in the previous case where we were checking if they do not exist. We're going to say vaults.member, and then we're going to pass that user ID. So this is going to check for us and see if that person is a member. If it's a member, it's going to allow them to pass and continue executing the codes that comes after their assert block. But then if they are not members, it tells them you have no vault position, right? And then what happens here is, now that we are sure that this person actually exists, we want to now receive the token they are sending to us. Now, to receive a token into a contract, you call, since we're dealing with shielded token, you have to call the receiveShielded function, or circuit rather. So this is the receiveShielded circuit. What it does is it allows us to receive a shielded coin adding validation conditions requiring this coin to be present as an output address to this contract and not received by another call. Now it allows us to receive that coin. You see, we have to pass in a shielded coin as an argument to it. And what this does is, behind the scene, this circuit calls some other circuit that have been defined by those who designed the entire compact code. So it calls that circuit behind the scene that goes to your wallet and requests that your wallet balances that transaction with that particular amount of token. So we're going to call this receive shielded circuit here. I think I misspelled shielded here. So receive shielded circuit, we're going to call it, and then we're going to pass it this coin so it can go and request the wallet to balance the transaction. It's this coin, this is as specified here. So we're going to construct this actually as a parameter and pass it here. It doesn't mean that this particularly is the coin. It's just a structure that describes the amount of coin that we want to take out. So whatever value the user passes here, we're going to set it as the value for that particular, like it is here. We're going to pass it as the value when we are constructing this shielded coin info. So yeah, once the user is depositing that, we're going to receive that token, and then we're going to pass in this coin, this closed coin. So with this, we have already received the token into the contract, but this still is not enough, because simply because we are receiving the token this way, it doesn't mean that the contract actually knows that we received it. Right, all right, it has received it, but then it doesn't keep track of it. Remember, I said when you're dealing with shielded token, the contract does not automatically keep track of it and tells you the balance that you have for each token, which is a lot different from what we have for the unshielded tokens. So what we do here is, in as much as we've received the token, we also need to add it to our ledger state to keep track of it here, which was why we defined this ledger state here before. So we have to add it here. And one last thing I noticed is, before we even deposit here, we want to also add another check to make sure that the coin type, the coin color that this user is trying to deposit is same as the specified token they created a vote for. We're going to say const vault. We're going to get the vault, this user's vault, and then we're going to get that using the same vaults dot lookup. We're looking for this particular user's vault position, and then we're going to pass in the user ID. We are going to use this to look out for this particular user's vault from our mapping we have, right? We are going to look for the user's vault position, and then we are also going to assert. We're going to check to make sure that the coin color, which means the coin color the user is trying to deposit, coin color. Remember, since this is a shielded coin info, we can access the color field. It must be equal to this vault, the actual coin color that was specified for that. Then I'm going to just try an error. Invalid coin type deposited. I have to close this also. Now we can go on, and since we've received it, now we have to also keep track of it, like I said, in our ledger state. So what we want to do is to insert this coin that we've received here into our mapping, because that's the way you update mappings. But for the fact that you actually we defined our ledger state to store coin infos, we have access to a few extra methods on this mapping. So let's look at what the documentation says about that. Data types. Let's look at ledger data type. I'm also going to be dropping a link to this in the description. So I'm going to be dropping a link to it in the description. So let's look for maps. So we would have access to this insert coin method. this insert coin method is accessible when you are storing coin UTXOs in your mapping. So you can see that we have to pass in certain parameters to be able to do that. So we said insert this insert coin method inserts a shielded coin into the map at a given key, where the shielded coin is transformed into a coin info. Now, if you check here, you'll notice that what we are receiving here is going to be a shielded coin info. And then since we are going to be inserting it, it's very proper that we use the insert coin method, and then it's going to take this guy and then convert it into a qualified coin info. So let's see how we are going to use that. Now, but before we insert it into the mapping, we want to check if there's another coin of that particular type that exists. Because if we're trying to just insert it directly, we might use it to override previous deposit of that particular token type that other users would have deposited. I'm not sure if you get me. So I said, if we're trying to just insert directly the new shielded coin info we're receiving, it's going to override any previous tokens we might have inserted. Remember, the default nature of insert is that it overrides the value at that particular point. So for that reason, we want to first check. Let me just say balance available. But let me use this case and just say if. And I'm going to shorten it for us. But let's do this. So what we are trying to do is now we are going to say we're going to look at our balances, and we are going to check if this particular coin we're trying to deposit is a member already. Coin dot color, right? If it's a member already, then we have to find a way of merging the previous coin we had before with the new coin. We need to find a way of merging the previous coin we had before with the new coin. You get? So but if that's not the case, we just insert it directly. So let's just, since that's if this is the first time, we're just inserting it directly. So we can just call balances dot insert coin. Remember, I said we have access to this simply because we are storing shielded coin infos or qualified coin infos in that particular mapping. So now we can just insert it directly if it's not a member already. And say at the instance, let's see the parameters we need to pass when we are dealing with insert coin. So when you are inserting a coin in the mapping, you have to pass the key type. And the key type in our case is the coin color, right? And then we also have to pass the shielded coin, which means the coin that we are receiving in that particular transaction. So in this case, this is it, the coin we've disclosed that we are receiving in this transaction. That's what we need to pass next. And then we have to specify the recipient of the coin, which in this case is going to be our contract address, right? So let's do that. So the first value we have to pass, we said, is the key type, which is the coin color, coin dot color, right? Then the next thing we said we need to pass is the coin in itself. So we're going to pass the coin, right? And then lastly, we want to pass the address, the recipient of the coin. And then in this case, it's going to be our contract address. How do you get the contract address inside of your contract circuit or anywhere inside of your contract? You have to run kernel.self. Now, this kernel.self returns you the contract address, the current contract address in which this circuit is executing, which in our case is our contract. So, but you can't just pass it to it directly, simply because it expects either this type or this, right? So there's a way to do it. Since there's a way to do it, to define an either type in compact, let's go back. To define an either type, you can use one of these two methods, either a right or a left or right. So you can see left constructor and either type, where the value that is expected to be provided is this, the left value here. While right does the same, construct an either type, but the value that is meant to be provided is this. So in our case, I'm going back. Yeah, since we are passing to the contract address, which means the value on the right, we have to use a right type. So I'm going to say right, and then I'm going to specify just to tell it the type of it. It's very important. Swap coin public key. We're going to see why this is so later on as we progress in the in writing the smart contracts. So contract address, right? That's what is expected, this or this. And now since we are saying this is we are providing the right value, so we have to pass in that kernel itself. This is how you insert a coin into a mapping. This is very strenuous as opposed to the case whereby if what we're doing is we just had a single qualified coin info, would have just updated what we had there. So now this is just for the case whereby that token does not already exist. But if it already exists, we want to match what we had previously with what we have now. What these are depositing now. So in that case, we want to look up const. We want to say previous balance. Previous balance. We'll call it previous balance is equal to. We want to look at our balances mapping, and then want to look up for that particular coin, right? And then want to specify the coin color type because we look up in our balances by the coin color. That's what we are mapping. So since we now have access to the previous balance, right, in the case whereby the coin already exists, what we want to do next is we want to match what we have previously, our previous balance, with our new balance. Something like we're trying to do our previous balance plus this our new coin balance, right? That's what we're trying to achieve here. Now, to match coin, you don't just do it by adding the amount. What you do is you have to use a special method called match coin immediate. There are two match methods, right? Two match method. We have one which is called match coin. What this match coin does is it takes two coins stored on the ledger and combines them into one. So it's taking two coins that are already stored on the ledger. And when we say coins stored on the ledger, we're already talking about qualified shielded coin info. Sorry about that. Qualified shielded coin info, right? Those are coins that are stored on the ledger, right? So you can see in this case, the merge coin takes in two qualified coin shielded coin info, which is not what we need at this point, because what we are trying to do here is we are trying to match an existing coin with a new coin, right? So in this case, we have to use match coin immediate, which means it's going to take a previously existing coin and then a new coin. This is qualified shielded coin info and coin info, since in this case they are talking about just unshielded coins. But in our case, we're using qualified shielded coin info, right? So we have to do match coin, right? We have to match this new value, right? We have to match the new value. Match coin immediately. Oh, since we're already doing this, right? It's easier to do it this way. What we do is we say our balances, right? And then we match then we pass in our previous balance and then our new coin. And then what this is going to generate for us is it's going to generate a new coin info, and then that is what we can insert into our mapping, right? So it's going to give us our new balance. This is it. It's going to give us our new balance. What is the result of merge coin immediate? Let's look at it. That's what I said. Coin info, or in our case, shielded coin info. So that's what we are going to insert here. So we are now going to insert this new balance. We are going to say our balances dot insert coin, and then we pass in the parameters we need. Coin color. We have to pass the coin color. That's the key, like we set here, right? We'll go back to the so that we see. Uh, let's go back to it and see. Okay. Map here is so our insert coin. We have to pass in the coin key first off, which we are doing here. And then we also pass the coin, which has to be a shielded coin info in our. So it has to be a shielded coin info. So that's why we had to merge it so that we have the new result becomes a shielded coin info. And then in our case, it's not going to be coin, it's going to become new balance. And then the last thing, we also have to pass the recipient, which is also same as this. Which is also same as this. So in this case, we are saying if the coin already exists in our mapping, we are going to take the previous balance and merge it with the new coin we are receiving to get a new balance using merge coin immediate, and then we are going to insert it into our mapping. But if that's not the case, we just insert it directly, right? That's the way to update um, um, shielded coin info that we are managing in our contract. There's an easier way to write this using ternary. So I think that's a lot much more easier. But if you understand this, you can write that in ternary. So I'm just going to leave it this way so we don't waste much of our time. Yes, so now that we've received our tokens inside of our contract, also updated our ledger state, what we want to do is we want to go on to uh we want to go on to um update our vault position now. So we're going to do const updated vault position. Updated vault is now equal to it's now going to be a new vault, right? But this case is not going to be an entirely new vault. We're going to pull the details of our previous vault by spreading. I can just spread our vault, the previous values of our vault, and then we update the values we want to update. In this case, we want to update the balance, right? We want to update the balance. That's the only thing we want to update. So we're going to say our balance now is going to be our previous balance, which is our previous vault balance, is our vault dot balance, right? Plus new amount that was deposited. How do we get the amount? We have to use coin dot value. Now, this is going to throw an error when we try to compile. I'm going to just leave that for now and then just insert. So we try to compile it and see the error we are going to get, and we'll learn how to fix it. So since we've updated the vaults now, we just go into our vaults and then we insert that new vault. Insert new vault, and then we have to pass in this same user ID, right? Our user ID, and then we have to pass in the updated vault. So this is going to override what we had previously, right? So now let's try compiling it and see the errors. I'm going to open my terminal over here. Then I'm going to run that command again. Run test compile. Now that's the error I'm getting. So it's saying mismatch between actual type is and declared type uint 64. So the declared type for this value property or vault is a uint 64, and then the value for the value property of our coin of our shaded coin info is a uint 128. So imagine you're adding a uint 64 and a uint 128. Definitely it's going to exceed the amount, right? It's going to exceed the amount. So what you might want to do is you might want to typecast it downwards, or better still, you might want to make this a uint 128. So it's the highest value possible. And then what we do is we just cap this in parentheses, and then we typecast it as uint 18, right? And then if we try to compile our code again, I'm sure we wouldn't get that error. Now our code compiles correctly without the error. I'm going to run it again so you see compiles correctly. In this case, we've been able to implement the two circuits we need for now: create vault and also to deposit um, tokens into a particular vault position. Lastly, we want to implement the circuit to withdraw um, value from our vault. So we also need to also specify a coin type, right? Or we do not even need to specify our coin. In as much as we are the ones calling the your circuit, we can also still declare derive our what's it called, user ID, the same way we've been deriving it since from our private secret key that's stored in our private state. Once we get this, we can also assert. I just don't want to keep on rewriting it. I'm going to copy this assertion line here. So we can also assert here and then see that this user has a vault position before we go on to withdraw. Now, once we've done that, we can also still take out this line of code here and then derive their lookup for their vault position. So we are saying lookup vaults.lookup for that particular user ID and get his vault position. Then what we can do is, since we have this now, we know the specific color and color of coin this user wants to. Now, to withdraw from a particular contract, right? There are specific helper circuits also, like the receiveShielded we have to use. But in this case, it's going to be sendShielded. So let me define it and then we'll go look up what sendShielded does for us. sendShielded. Now let's go and look up what sendShielded function does for circuit. So let's look for sendShielded. Now this is sendShielded. You see it's written here that sendShielded sends a given value from a shielded coin owned by a contract to a recipient. It allows us to send tokens from what we have in our contract to a particular recipient, and any changes is returned and should be managed by the contract. What this is telling us that it sends from our balance we have on the contract, and the changes that we are going to receive, it has to be managed by the contract, and we don't expect Compact to manage it automatically for us. We have to devise a mechanism to also manage the token that is the balance that is returned. So this is it. sendShielded, it takes in the input UTXO, that's the qualified coin shielded coin info that we already have stored on chain, and then it takes in the recipient address and the value we want to send. So it sends it to the user and then returns a shielded send result. A shielded send result. And then let's look at what a shielded send result is. Or better still, let's go on to implement that first off. Now, we are going to send this person, when they want to withdraw, they have to tell us the amount of tokens they want. Amount they want to withdraw from their vault. So it has to be a uint 128, right? So we don't have to typecast. So they specify the amount they want to withdraw, then we can disclose the amount where we want it. So what we do is since I'm going to be using this amount several places, I'm going to disclose it here. Say amount. And then this, I'm going to put an underscore here. So I'm going to disclose that amount we are receiving, and then we can use it wherever we use it. So what we're trying to do here is we're going to pass. We said sendShielded takes is it that let's see. Yes, sendShielded, the first value it takes is the balance, the existing token that we already have. In this case, we have the existing token, but it is stored as a mapping, right? So we have to look for balance we want to send from. Let me call it balance to send from. And then it's going to be balances dot lookup Let's look up our vault. Then we can take out the coin color property of it and then use it to find it. So we have that balance to send from. That's what we're going to pass. Because this balance to send from now is going to be qualified shielded coin info. That's what it's going to return to us. Now we are passing that balance we want to send from. And then the next property we have to pass is parameter rather has to be a recipient, either this or this. Now in this case, if you remember, I said when you want to pass a recipient to any of the circuits, you have to use an either this, and there are two ways to construct it. We have left and right. In this case, since we are sending to a user, which is the right, I mean the left parameter of this type definition here, so we have to use a left right. So that's what we're going to use. We're going to say left, and then we're going to call the left circuit, and then we're going to pass these same properties here that we passed initially. Z-swap, swap coin public key, and then the contract address. And then we have to pass the address, the public key of this person that is going to receive this token. In this case, this is the user who deposited it. Now to get the user's own public key, public key, so we can send the token to them. We don't have to receive their address. What we can do is Compa gives us a utility circuit that allows us access an encrypted encrypted version of the user's public key, and that is called the own public circuit. So let's see what own public key does for us. Let's look it up here. This is own public key in the documentation, and it returns to us a Z-swap public key of the end user creating this transaction. So whoever is calling the circuit, this own public key returns to us the public key of that, the Z-swap public key, which means the encrypted public key of that user. And then we can use it to send tokens to them. So we are going to call that method, and then it returns to us the Z-swap coin public key. Now let's see what a Z-swap coin public key is, so we understand as well. A Z-swap coin public key, we said the public key used to put shielded coin info to a user, used as a recipient in shielded and all of this. So it's the public key they use to receive. A recipient can use, a user can use to receive tokens from. So that's it. So we are passing this, and then back to the previous circuit we trying to use. Okay, send shielded. We've passed the balance we want to send from, balance to send from, and then we've also passed the recipient, which is user. Lastly, we have to pass the value, which is the amount this user is trying to withdraw. There's going to be amount, right? It's closed. And then this is going to return to us the balance, send shielded result, like we saw in the definition just now. We said this returns to us the shielded send result, rather. So we'll call it results or send results. Now, since we have this send result, let's see what send result looks like. This is what send result looks like. The send result is the output of a send shielded or send immediate shielded, detailing the created shielded coin and the change from spending. So it's the send shielded result is more like an object that defines the result of a particular send transaction, which includes majorly the change, and that's what we are mostly concerned about. Because if we are storing several users token of a specific coin type in a particular place, we want to also know that when we send to that user, we want to manage the change side of it, which means we are more concerned about this change. We can check for this. Now, what does the change look like? Now, this you said the change is maybe a shielded coin info. The change is maybe a shielded coin info. And what does maybe present? Maybe is used to encapsulate optional presence of value. So we can assess each of these properties. So the change now is more like if it has this is some property which tells us, which is a boolean and tells us if there is actually a change, whether it's true or false. And depending on that, we can know whether to update our state or not. And then it gives us the value, which is of the type that is passing to. In our case, the shielded result, shielded send result returns to us uh, the change of maybe type shielded coin info, which means we are going to have a boolean that tells us whether there's a change, and also if there's a change, we are going to have access to that change, which is shielded coin info inside of it. So we're going to check here and see if the send result dot change dot is sum, which means we're accessing the boolean property of that field. I'm using underscore underscore is sum here, right? This is sum underscore sum rather, and this is intentional because I think this is more like an omission. Midnight compact developer meet. He thought they changed it to is sum in camel case, but that's the opposite. It's still left as this is underscore or underscore sum. So we're assessing that boolean property. Then we are saying if there's a change, which means if this is equal to true, then we want to update our balance just the same way we updated it before. But then if there's no change, we just want to remove that stuff from our map, right? So what we want to do is say else if there's no change, we want to remove that token from our mapping. So we can just do balances dot to remove, and then we can remove that particular token type. So can say vault dot coin color, right? We can remove it. But then if there's a change, we want to update our balance. I'm going to copy this code here so I don't spend time rewriting it. Then bring it over here, paste it. Best case scenario, what you want to do is you extract this logic that is meant for sending and receiving, updating your balance into a separate circuit that you can just call everywhere, so you don't have to keep repeating the same block of code. Okay, in this case, right, we are not merging. Since we are not collecting a new coin info, we are just straight up storing the change, updating our balance with the change, because what is left is what we have entirely of that particular token type. So we are just calling balance.insert coin. But instead of this coin.color here, since we don't have access to coin here, we can call vault.coinColor, right? And then our new balance is going to be our change, not we're not merging anything here. So it's going to be our send results, change we are collecting dot change dot value. Send result dot change dot value. Why is it dot change dot value? Let's go back. We said sendShielded, right? Returns to us the sendShielded result. And the sendShielded result is of this type. It tells us it gives us the change if there is any, and it tells us the amount that was sent. Our major concern is the change, since we have to manage our change by ourselves. It was obviously stated. So our change is maybe a shielded coin info, and maybe is a struct on its own that receives a generic type, which is in our case is this shielded coin info, and then it gives us access to it. It allows us to optionally see whether a value is present or not. So if that value is present, if we have a change, that's what we are saying here. We have a change, we want to update our contract to keep track of the current balance and not the previous balance. So we don't have people overdrafting, like withdrawing more than what they have in the contract. So what we are trying to do is we are taking that change. If it's true, if it's sum, we're taking that change and then we are passing the value, the new value, which is the new token balance that is returned to us. In our case now, since it's shielded coin info we are passing here, our value becomes shielded coin info, and then that's what we are going to store here. So it becomes send results dot change dot the value. It's the value. But if there's no change, we just remove it. And with this, we've come to a conclusion of our smart contract. Let's try to compile code again and see what we have. I'm going to open my terminal. Let's compile. Okay, there's an error somewhere. Here, passing on public key. It says unbounded identifier simply because I typed it wrongly. It's supposed to be own public capital P and key capital K, just in camel case. Let's see if we have any other. Now we don't have any other error. Our code compiles successfully. So this is all you need to implement a smart contract app for a Vault DApp. Sorry, I'm sure at this point we've learned how to interact with um tokens. Thank you.